International Math Olympiad 2013. Problem 6. Let n not less than 3 be an integer and consider a circle with n plus 1 equally spaced points marked on it. Consider all labelings of these points with the number 0, 1, etc. n such that each label is used exactly once. Two such labelings are considered to be the same if one can be obtained from the other by a rotation of the circle. A labeling is called beautiful if for any four labels A less than B, B less than C, and C less than D, with A plus D equals B plus C, the chord joining the points labeled A and D does not intersect the chord joining the points labeled B and C. Let capital M be the number of beautiful labelings, and let capital N be the number of ordered pairs x and y of positive integers, such that x plus y less than or equal to n and x and y are coprime. Prove that capital M equals capital N plus 1. This is a good counting problem. We basically need to count all beautiful labelings for any given natural number n. Let's define some terms and make some obvious observations. Since rotation around the circle does not change the labeling, we can, without a loss of generality, list the labels in any labeling starting with label 0 and going in the clockwise direction. All the numbers that we will be working with are non-negative integers. The expression one label is after the other means that the first label is further from 0 in clockwise direction. The expression balanced means that a quadruple A, B, C, and D has the property that A plus D equals B plus C. A balanced quadruple is invalid if it's arranged in such an order that the sum of the first and third labels equals the sum of the second and fourth labels. A labeling is beautiful or valid if it doesn't have any invalid quadruples. We must understand that the conditions of this problem impose severe restrictions on labelings. If we can show that at least one quadruple in a labeling is invalid, that makes the entire labeling invalid. For example, labels 0 and x, the first label placed after 0, are part of arithmetic progression which includes all multiples of x in this labeling. This allows us to eliminate all labelings in which at least one pair of two consecutive multiples of x is arranged not in monotonically increasing order. It's shown on this diagram that the quadruple that includes two consecutive multiples of x and two fixed labels 0 and x form a balanced and invalid quadruple. So any valid labeling must have all the multiples of label x be arranged in a monotonically increasing order. For the same reason, all the numbers in a valid labeling that have the same remainder modulo x must also be arranged in a monotonically increasing order. This diagram shows that any two consecutive labels with the same remainder modulo x, not in increasing order, and two fixed labels 0 and x form a balanced and invalid quadruple. So we have identified in any valid labeling that starts with 0 and x groups that start with 0, 1, 2, etc. up to x minus 1. And in each group, the labels are arranged in the monotonically increasing order. We will also prove that in any valid labeling, these x groups must be kept separately without overlapping each other. For that, we will prove first that two consecutive numbers that have the same remainder r cannot be placed between two consecutive multiples of x. On this diagram, we have two consecutive numbers jx plus r and j plus 1x plus r between the two consecutive multiples of x, ix and I plus 1x. If we connect them with chords as shown on the diagram, we'll see that they form a balanced and invalid quadruple. Analogously, we can prove that two consecutive numbers with the same remainder p modulo x cannot be arranged between two consecutive numbers with a different remainder r modulo x. These two facts will help us to prove that any number r that is greater than 0 and less than x must be placed after the highest multiple of x. And since all numbers that have the same remainder r modulo x must be arranged in monotonically increasing order, that means that all such numbers must be placed after the last multiple of x. This is easy to prove. Suppose that r is placed anywhere between x and kx, which is the highest multiple of x. Let number p be x minus r. The label k minus 1 times x plus p must be after kx, since all labels with remainder p must be arranged in monotonically increasing order, and not more than one of these labels can be placed between each two consecutive multiples of x. This is the kind of pigeonhole problem where no more than one pigeon is allowed to sit in one hole. Then numbers 0, kx, r, and k minus 1x plus p form balanced and invalid quadruple. Let's assume that number n equals kx, so that each group of labels, including the group with remainder 0, have equal number of labels. We will prove that no two different groups of labels can overlap and form a valid labeling. If number r that's less than x is the first label after kx, and p that's less than r is placed anywhere inside the group of numbers with remainder r modulo x, then the highest number with remainder q, such that q plus p equals r, is after the highest number with remainder r, so that this highest label k minus 1x plus q, along with labels p, k minus 1x plus r, and 0, form a balanced and invalid quadruple. If in the same situation p is greater than r and q plus r equals p, then the highest label k minus 1x plus q forms a balanced and invalid quadruple with labels r, p, and k minus 1 times x. Let's use mathematical induction and assume that several groups of labels with different remainders are placed after kx, and none of them is overlapping with any other groups. And remainder r is the first label after these groups. And assume that there is a different remainder p that is placed inside the group r. Then in case 1, the balanced and invalid quadruple is either the same as we saw in the last diagram for this case, or is formed by p, q, r, and 0. And in case 2, the invalid quadruple is either the same as we saw in the last diagram for this case, or is formed by labels k minus 1x plus r, q, p, and k minus 1x. The statement in this diagram formulates the key discovery that follows from all our previous results that will help to solve this problem. If x is the first label after 0, then any valid labeling with number of labels multiple of x must have exactly x non-overlapping groups, of which the first group consists of labels multiple of x in monotonically increasing order, and any other group consists of monotonically increasing numbers with constant remainder modulo x that's unique for that group. Each of these groups begins with the lowest number that is less than x, and the very first such group that follows the group of multiples of x, let's call it y, forms the arithmetic progression, which has the first two members, 0 and y, and consists of numbers multiples of y. The picture on this diagram shows that any pair of consecutive multiples of y placed not in increasing order forms a balanced and invalid quadruple. If numbers x and y happen to be coprime, then according to Chinese remainder theorem, for each positive number r less than x, there is an integer number such that its remainder modulo x equals r and its remainder modulo y is 0. And that number is unique in interval 1 through y times x and periodically increases in each next such interval I times yx plus 1 through I plus 1 times yx. So, to select the next group that follows the first group that contains remainder y, we must calculate remainder of 2y modulo x and select the group that contains that remainder. Then number 2y will be placed after number y, as it should be. Then we must follow the same procedure and calculate a remainder of 3y modulo x and select the group that has that remainder and continue this process until we select the group that contains the remainder modulo x of number y minus 1 times x. This process will select exactly x minus 1 groups in this prescribed order. This diagram illustrates construction of a beautiful labeling with 11 labels, not counting 0, that uses our prescribed procedure. In this example, x equals 5 and y equals 3. As the first step, we have constructed valid sequence with 5 times 3 labels, not counting 0. Then we have determined the order of groups of remainders. The first group starts with remainder 3. The second group is the one that contains label 3 times 2. The next group is the group that contains label 3 times 3. And the last, fourth group, contains the label 3 times 4. Then we have selected all the labels from 0 through 11. Notice that the last multiple of 3, 12, is not part of the resulting sequence. However, the group that contained label 12 still determines the order of its group. This group contains labels 2 and 7, and it's the last group in this valid sequence. Two consecutive multiples of y have different remainders modulo x. Let one of these numbers be j times x plus r. In this case, the next consecutive multiple of y is either jx plus p or maximum jx plus x plus p. Then it's easy to calculate that in both cases we have balanced and invalid quadruples, even if the number of labels in this labeling is not big enough and doesn't actually include the two consecutive multiples of y. This labeling is still invalid if it violates the prescribed order of groups. We have proved by now that if the number of labels is multiple of x, and x and y are coprime, then only one valid labeling with prescribed order of labels may be possible. But we haven't proved yet that this unique labeling that is forced by selection of two numbers x and y is actually valid or beautiful. Let's prove it. If four numbers belong to the same group with the same remainder r, then they are part of the arithmetic progression that is arranged in monotonically increasing order. And clearly, such four numbers cannot be an invalid quadruple. If three numbers belong to one group with the same remainder r modulo x, and one number is part of a different group with a different remainder modulo x, then obviously such quadruple cannot even be balanced. If two numbers belong to one group with remainder r and the other two numbers belong to the other group with a different remainder p, then we can assume without the loss of generality that one pair is arranged after the other, and such two numbers cannot form an invalid quadruple because each pair is arranged in monotonically increasing order. If two numbers belong to one group with the same remainder r, and one number belongs to a different group with remainder p, and the fourth number belongs to a different group with remainder q, then clearly such four numbers are not even balanced. If four numbers belong to four different groups with four different remainders, then each of these numbers has the same remainder modulo x as some multiple of y. And as we know, these four groups are arranged in monotonically increasing order of multiples of y. Then, not too complicated modular arithmetic proves that such four numbers cannot be an invalid quadruple. We're almost done. We have a couple of items of unfinished business. What we have proved can be formulated like this. Any pair of numbers y and x, where x is greater than y and x and y are coprime numbers, defines the unique infinite valid sequence of labels that has the group of labels x, 2x, etc. to infinity in the beginning, followed by the group of labels y, x plus y, 2x plus y, etc. to infinity, followed by x minus 2, similar group of labels with different remainders modulo x in the prescribed order. This infinite sequence can be constructed by creating the unique valid sequence with x labels, then expanding it to the unique valid sequence with 2x labels, etc. to infinity. This can be done since we have proved the existence and uniqueness of a valid sequence with any number of labels that's equal to a multiple of x. Then for any positive n, the valid labeling with n numbers of labels defined by the same pair x, y can be created by simply selecting the subsequence of labels 1, 2, etc. up to n in the same order they appear in this infinite sequence. This proves the existence of one valid sequence with n labels that corresponds to the pair x, y. You can try as a home exercise to formally prove that there are no valid sequences with n labels other than the subsequence of the unique infinite sequence defined by our prescribed procedure. We have not yet addressed the question what happens if y is not coprime with x. We can look at this example. X equals 4 and y equals 2. 4 and 2 are not coprime, and we can see that both possible arrangements of the remaining labels 3 and 1 produce balanced and invalid quadruples. You can also try as a home exercise to formally prove that such arrangement cannot produce a valid sequence. The last trick of this problem. We need to convert our formula of counting the valid sequences to the format used in the question of this problem. When we count the number of valid sequences, we need to start with the case when x equals 1. In this case, there is no y, because the entire valid sequence consists of one single group of monotonically increasing multiples of 1, which is 1, 2, 3, etc. up to n. This trivial sequence counts for 1 in our formula. For all other values of x that start from 2, there is y, which is any positive integer less than x and coprime with x. So number m of valid labelings for any given n not less than 3 is number of all coprime pairs x, y, where y is greater than 0, x is greater than y, and x is less than or equal to n, plus 1 trivial labeling. Obviously, for any pair x, y, where y is less than x and y are coprime, exists corresponding pair x and x minus y, where x minus y is also less than x and is also co-prime with x. So the number of such pairs equals the number of corresponding pairs x minus y, y, and y x minus y, which are also co-prime with each other. Thus, the number of all co-prime pairs x and y equals the number of all ordered co-prime pairs y and x minus y, whose sum equals x, which is not greater than n. We're done.